Hello, everyone. Welcome to this session of the MLOps conference. My name is Aslı, and I work as an applied machine learning engineer at Algorithmia. But today, I'm very happy to be here and volunteer for the MLOps community to introduce one of our many brilliant speakers. Before we start, I'd like to remind you that if you have a question regarding the talk, please post it in the chat. And when the presentation ends, I'll be asking those questions to our speaker. Now in this session, we have Joao Da Silva from Avast, and he's joining us from the beautiful city of Prague. Joao is a public speaker in Spark Summit, Data Summit, and local meetups, and he's a meetup co-organizer in Prague. He's been involved in the data engineering field for a while, and he's a functional programming lover. He's currently architecting the MLOps platform and strategy for Avast, so they can provide a safe online environment for the wider population. So please join me in welcoming Joao, and now I'm be passing the microphone to him.
Thank you very much for a fantastic introduction, and I'd like to say thank you to everyone which is online in this session. Today I'll be talking about MLOps platform architecture that we use at Avast for delivering end-to-end machine learning pipelines. I'm Joao, and fantastic introduction. I'll skip that. So what is Avast? Avast, we are dedicated to creating a world that provides safety and privacy for all, no matter who you are, where you are, or how you connect. We try really hard to protect people online in this day and age. The goal of today's presentation is to guide you through our journey and how we progressed in implementing MLOps technologies and MLOps principles so that we can deploy and manage machine learning pipelines. So the quick agenda view will be just touching on Vitruvius Theory. What is that? We'll be exploring the environment in which the architecture I'll be presenting it's involved, the context or the foundations which we build upon. Also, I'll be talking about the golden ratio of MLOps architecture for us and what we really needed to achieve, and of course some building blocks, what we use, what technologies, and how we actually deliver. And in the end, we'll be showing you the actual architecture, the final architecture, or the current end product that we worked on. But before I go any further, I'd like just to put down what is architecture. And architecture is how you organize a set of building blocks within an architectural model that satisfy a specification, and therefore connecting those blocks within to meet the overall requirements of any system. So what is Vitruvius Theory? Marcus Vitruvius was an architect from 1 century before Christ from Rome, and he had 3 principles for good architecture. They were strength. If you architect something, they must be strong. It must have utility within the society or within the ecosystem, and it must have certain beauty. And as a continuation of this talk, I'll be talking about how these 3 values were taken care of within our vision in our platform. So what is the environment? Before you start creating anything, you need to study your environment. And as in a MLOps environment, is that the most important are the people. And there are 3 personas in the MLOps that we identified. Is the data engineer, the one responsible for the data, ensuring the data is ready, data is clean, data arrives successful, the data lakes are supported, are maintained, and the data is moving across the systems. Then, of course, we have the researcher or the data scientist. Those are the ones that produce the business value, they develop the models, they explore the features, they explore the data, and then they create something of value. And certainly, there is upcoming, perhaps one can say, discipline, which is the ML engineer, which is the intersection of these 2 worlds and is capable to understand these 2 worlds and produce real value, the delivering machine learning into production. But of course, within the organization, in Avast, for instance, there was a cultural shift. There was the shift where the leaders decided that we need to improve our machine learning operations, therefore MLOps, and that all these three personas must and can interact in a productive way and ensure the ultimate goal that the machine learning engineer has everything he needs to be successful to deploy those models. But as part of the architecture point I mentioned earlier, there must be an architecture model, right? We don't create something out of dreams. Why not? But there must be some architecture model. And the maturity model in MLOps is a strategy that clarifies the DevOps principles and practices that are necessary to run successful MLOps environments. And an extra added point, it helps the organizations to identify gaps in the implementation and what they can achieve. A quick recap on the maturity model is the level 0, where there is no MLOps. Many organizations were there. We were there, where most of the work is manual, data is copied, CP data from one place to the other. The researchers execute the work on their current local laptops, and at the end they send the model somewhere and somehow it happens. Then you have the next level up, where organization already has some DevOps facilities. So there is a DevOps system. They have a Kubernetes cluster where they can deploy models, but it's still not real MLOps because it's not focused on the machine learning. Once you go a step further, you actually can automate your training. Somehow you have a scheduler, you are able to take the data from A to B, compute your features, produce a model, and doing so in an automated way. But that is not enough, because we want to have automated model deployment. It's not enough to just have it automatically training, but then send it over the fence, give it to some data engineer, give it to some deployment engineer, and then they will take care of deployment. No, this should be automated. Once you are there, you are at the level 3 of the maturity model. Finally, the dream of the organization is to have full MLOps automated operations. This means once you have the model being automatically deployed, you should also want to react on it. So you should check your concept drift. How is the data flowing? How are the predictions going? Was there any changes on the incoming data for which the model doesn't understand? And if it does happen, how do you react to it? Do you trigger some events? Do you alert for retraining of the model? Once we are there, then you have full MLOps automated operations, from beginning on the training to triggers where you can retrain your model based on drifts detection. At Avast, at the moment, we are in a transition into the level 4. I will touch that later on, but we are at automated model deployment, hence the title of this talk, end-to-end machine ML deployment. So, golden ratio, what does it mean? So we mentioned earlier that we have this maturity model, right? But in fact, it's not enough. There's a lot of things to achieve it, and you cannot tackle all of them at the same time. So you have to prioritize what you would do, what you will do. Hence the golden ratio. What was our golden ratio, or at the time we called it golden path? We needed, and we know that we needed to be able to orchestrate our workloads in many different systems. So we wanted to set a task on a cluster A and then another task on the cluster B, and then put the data together and so on. So we wanted this ability. We also need to manage these workflows, right? Because ultimately, this has to be managed. We don't want to write hand by hand all the time. We don't want to have repetitive workflow management. So we want to have a way to manage this workflow. Also, we needed to have to manage the models and to track the experiments. This was one of the main requirements and what MLOps is mostly about, in my opinion. Of course, we had to do and support all of the above while reducing complexity. And by applying all those principles, we wanted to be able to scale the machine learning processes, because we wanted to go from the level 0, where there were some machine learning which were manual, or they were on the level 1 where there was somewhat a deployment. But we don't want to have to repeat ourselves and do one by one. We want to have a way where we can scale this and automate it and just scaling. And of course, the ultimate goal is to have these end-to-end pipelines where it goes from training to deployment without human intervention. But before I explain the actual architecture, there is some context. Avast in particular, which might not be fully standard, is that we run everything on premises in our data centers, which creates some challenges in the way that we could not go into the cloud vendors and take some of the off-the-shelf products. We needed to take what we had and create our own MLOps platform. Some of the things we have is quite standard, but I'll just run them through, which is we had a couple of Hadoop clusters, some GPUs clusters and CPU clusters where the different computations are executed. We have in-house Minio storage for S3 compatible storage, and we have a deployment target as Kubernetes. This is the foundations in which we had to build our architecture and our platform. So what were those building blocks? We chose Airflow for the goal of cross-system orchestration or scheduling. Because Airflow architecture provides a message, it's message-driven, in which through the RabbitMQ or the message queue, we can schedule different tasks in different machines, in different clusters. And this was one of the key facts why we chose Airflow. But once we chose it, we also learned that it was quite extensible. It's Python, and it has a lot of small features, which allows us to remove some boilerplate. If you know Airflow, like you have default arguments, you have some templating and whatnot. Next, we went into the market and we wanted to track and manage our experiment. And at the time, MLFlow was the choice. We gave it a go. It was extremely simple to set up. It's open source, so you can go into the GitHub and you can find out what issues are open. You can identify what is lacking or what is being tracked, what is being worked on. It's very easy to track the experiment. It's their API is very rich. Also has this CLI, which gives us multiple features that are useful. And also important aspect for us is the model packaging. Because with MLFlow, we have the standard structure, and you can deploy almost any kind of model in a standard way using the MLFlow serve, for instance. And one other important thing for us is the version of management of the models, because through being able to manage the versions of the models, we can then react on it and manage and trigger deployments. Which brings me to the next point. MLFlow is great, but it has something that is lacking at the moment. MLFlow does not have event-driven architecture. It doesn't produce any events. It does have a fantastic REST API, but it does not provide events. So we created what we call MLFlow Deployer, which is a service that is aware of all the models that are registered into our MLFlow instance. It picks up the differences between the model versions. So if you register a new model and you give it a status or a staging or production, then this service reacts on it and puts together the metadata that is required to complete the deployment. And once it has the metadata, it can produce deployments in two different ways. The GitOps fashion, which you just open a pull request into a Git repository, and then someone responsible would take care of it, because not always it's required to have an end-to-end deployment. So that's the option. The other reason why we have the GitOps approach is that and open a pull request with the metadata is that in some cases you want to do inference which is offline, and for those cases providing a file to a repository where is the actual job that is run. It's very useful. And also we provide the continuous delivery way where we just send a request to our TeamCity platform, and the build is triggered and deployment happens based on these metadata such as artifact URI, artifact version, and whatnot. And it has a bonus because we now have an aggregated view of the MLFlow models and which ones are deployed, which ones are not deployed. This service also provides a REST API that can answer to simple questions such as what is the latest model that is deployed in production, when was it deployed, and so on. So it's a crucial part for the end-to-end pipeline and deployment. Next up, if you know Kubernetes, there is the lack of templating. So we selected what MLOps Helm. If you're not familiar with Helm, just a way to template Kubernetes deployment manifest. And for us, it has many benefits. First, integrates very well with our continuous deployment system because we can just trigger this deployment. You have these variables as input from our deployer, and the Helm chart knows how to transform that into a Kubernetes manifest. So therefore, it also reduces duplication because we don't have to rewrite the same Kubernetes manifest over and over. We just say, use this Helm chart. And like I just mentioned, integrates with deployer metadata. The one other extra benefit is that this way we have consistent deployment. There is no difference between the manifests. They are generated in the same fashion with the same templates. So this way we guarantee consistent deployments and configuration. Next up, one thing that we had to do for our platform to work was Docker. And MLOps Docker is a repository where we created some base images for different workloads, such as TensorFlow and GPU, MLFlow serving, different Python environments with the poetry and whatnot. Also, images that wrap some services or wrap some binaries that allow us to do some tasks that are repetitive. So if you want to sync data from Minio to HDFS, or if you want to copy data around, is one of the images we provide to remove repetitiveness. If you want to submit a Spark job to remote Spark cluster, it's also there, the Spark launcher and others. Just one last one that we have now is that we are deploying Julia models, and we also provide this base Docker image for Julia ecosystem. Next up, it's something that we are currently working on, but we found extremely important, and this is what will allow us, with some degree, to progress into the last level of MLOps maturity model, which is the ability to detect drifts in the data, detect outliers, and some degree explaining the machine learning models. If you don't know, check out Alibi Detect library, for instance. But all of the tools above and all of these building blocks, they do a purpose, they work well, but in isolation, they just give us the strength that I mentioned from Vitruvius. With this, we have the strength. However, we don't have the full utility, the full usefulness, because it's different systems which are separate. So we need somehow a tool that would connect them together. And this tool should, and in ideal, should prescribes the common understood structure, so that if we change from project A to project B, there is a common structure that is understood across the company. For researchers' point of view, we don't want them to spend too much time thinking about how I deploy something to server A or to server B. How do I get cluster GPU cluster access and this sort? So we don't want we want to abstract the infrastructure away from researchers to simplify their lives and let them focus what is important. Also, like if you have a machine learning pipeline or workflow, you have different stages. You have to manage those stages. You need to validate that the stages are actually connect together. You have to also, in some cases, you want to query how does the model is at the moment. So if you want to know, I want to know where is the dashboard for model A. So we want to be able to find this easily from a tool, not from some documentation. Of course, we also have it, but having a tool that provides us this, it's very useful. The tool also should bridge the gap between the research and productization. You should format an ecosystem or a world, a small piece where everyone understands what is going on, and it will facilitate moving from research to production. And the ultimate goal of the tool as well is so that all the personas in the MLOps environment can participate and collaborate around that same tool. What kind of tool can do this? The CLI, Command Line Interface. It's from the 60s, and for me, it's still today one of the most beautiful user experience that exists in computing. And we decided to write a command line tool that would do this for us. But what does it actually do? So our command line tool for MLOps manages the pipelines. It prescribes the said common structure across the machine learning project, because having this tool, it expects a structure, a directory structure, it expects certain files and certain configurations. So it's a configuration over convention in this case. It operates on a simple YAML grammar. So this YAML grammar is the configuration aspect. It builds, validates, and pushes the Docker images that are used to execute the code for the pipeline. So, and it does so in a transparent way for a researcher or for anyone working on an MLOps CLI project. They don't need to wonder how is the Docker build, is it validated, is it published, where is it published, and so on. So the tool does that for the researcher. Because I mentioned earlier, we use Airflow to execute our workflow. So this tool takes the configuration, generates Airflow DAG, executes the integrity tests on the Airflow DAG, and it pushes the DAG into the Airflow repository, which is then automatically merged upon successful build. So this removes, this makes it really fast to go from publishing your pipeline to have it deployed into Airflow and being executed thereafter. And of course, in a continuous deployment, continuous integration world, there must be tests, and this tool helps the researchers to write the tests and execute the tests. But the key important piece here is that the tests are executed in a continuous integration way, and they are executed in the Docker, the same Docker images that are built, validated, and pushed. So when you execute code on the cluster in a Docker image, you know that you have more guarantees that your environment is correct, because you run the tests in that same image and that same environment. And by having all of this together, it helps and it promotes consistent environments, because by having this recipe or this prescription, by having Docker as the underlying image, by having a well-documented YAML grammar, right, and by transparently pushing these DAGs into the servers with the tests, it just makes the ecosystem and the environment where the code is executed more consistent. So how does it look like from the user experience point of view? It all starts with the cookie cutter template, where, as you can see in the slide here, you have the prescribed repository after you execute your cookie cutter. So you can see that you have your workflow.yaml, where you describe your actual workflow. You have your tests.yaml, where you describe your tests. Important here is that we try to keep the grammar of the YAMLs as small as possible. It's an important point. And then, of course, you can see on the Python package point of view, you have a stage and you have train.py, and it's common to have stage and infer.py and so on and so forth. So this way, all of the code is executed and is laid out in a structured and common way that any project within the MLOps ecosystem has the same format. So if you transition from project A to project B, you don't need to learn everything how to get started because you already know at least this part. And you can focus on the internals of the code in your logic and you don't need to focus on the outside aspect. And also the CLI is the simple interface. So if we go back to Vitruvius, this is the beauty that through with so much requirements and with so many tools, so many building blocks, we somehow managed to reduce it to this shorter example where you just execute your workflow build, which will do what I said, build the Docker images, publish, and whatnot. You can run your tests also with a simple command line call. And I put the other one down there, the workflow push, because this one is used mostly by the MLOps, by my team, by our team, where we can actually push and is executed by the continuous deployment system, the continuous build and deployment system. So this is where the Vitruvius beauty come into place. So I will now just quickly jump into another tab, and I will show the architecture diagram, the overview of what we have today, because the slide is quite hard to put them on slides. So I will just quickly switch tabs. I hope everyone is aware. Before we start exploring the diagram, for the last few minutes we have, just the blue represents the researcher, green is us, the MLOps, orange is the continuous integration tool, CLI is the CLI I just mentioned, it's what it does, and clusters is just the computation where we have. As you can see, from the researcher point of view, we reduced to these 4 stages where you get started with your cookie cutter. The researcher updates their workflow.yaml, he adds their sources. You can also run notebooks through Papermill and whatnot, and they are in the circle there. And then they just workflow build, workflow test. Once they have it passed, they can do the git push to their repository, and the build push tool from the continuous integration will do the rest. We'll build it in the continuous integration system and we'll push it and deploy. I will just also highlight here this particular aspects, just to summarize it. Visually, what does the CLI tool does? Just builds and validates the images, runs integration tests inside the validated Docker images, builds the Airflow DAG and tests it against integrity tests on the DAG. And then this also provides that consistent environment, abstracts the infrastructure, and the interface is declarative. What is next? So once we get our DAG to Airflow, and we are able, because of Airflow and because of the nature of its architecture, message driven, we can access any, and we can target any cluster where the computation is run. And assuming that the researcher does logs a model or registers a model here into the MLFlow registry, we can then visualize the important part that makes it end-to-end. Because you can just register a model and you can do it also in a different way, but it doesn't finish there, right? So this is where the deployer service come into place, and it's the interface for our deployments. Let me scale up. It caches the information about the model, it updates the status, and triggers deployment actions that are executed. Once we go through the deployment setup, we are able to, well, have it deployed into the MLOps serving, in our case, Kubernetes, And on the top hand side here, I'll highlight it so it's not confusing. We have those Helm charts, as I mentioned, integrated with our Team CT DSL that are able to understand the deployer metadata. The aspect that we are now working on this architecture point of view, this is a work in progress that I introduced earlier, this MLOps alibi for data drift, concept drift, and so on. So in our monitoring, we call it the MMF, Model Monitoring Framework. It lives in here, and from there, our goal is a work in progress, but our goal is to have the triggers calling back to our, sorry again, I'll just pop up. Our triggers calling back to Airflow REST API and say, well, we detected drift, retrain our model. So I'll switch back to the presentation. Sorry for that. The conclusion for this talk at the moment is that through this architecture, either by the building blocks we chose, which brought us the strength from Vitruvius Theory, then we made it usable and we brought the utility and the beauty by using the CLI and the workflow grammar, a simplified YAML grammar, which abstracts away many of those tools which are the building blocks. So we reduce time to delivery and the complexity. Following this strategy, which the golden ratio I mentioned earlier, which were the crucial points, we improved our MLOps maturity levels, which means we didn't start from the top down and follow 0, 1, 2, 3, 4, but we actually identified what we really needed to get started. It's actually interesting that when we got started, we had a project, we took it on, and we identified this project needs this piece, the other piece, next piece, and we build on it, and therefore we improved it. We currently have at Avast, using this architecture, we do have end-to-end pipelines, machine learning pipelines, where the researcher does the changes, the git push, the scheduler triggers the build, triggers the DAG, it completes, it logs the model, and once the model is logged through the metrics from MLFlow, we are able to identify if the model has the correct accuracy, if it matches, if the metrics matches what we expect or the researcher expects, and based on that, we register the model and change the model status to stage or to production, depending on the situation. So, and then the rest of the pipeline kicks in and deployments and things happen. So we do have end-to-end machine learning pipelines. And one of the most rewarding things for this particular architecture and solution is that within other teams at Avast, we get interest to adopt our solutions, because it's sometimes hard to. There was a cultural shift, but there is still ongoing to bring more teams on board and to there is sometimes an effort to sell to other teams and say, give it a shot, try our solution and see how it ends. But there are already interest for our solution. Finally, just a quick thank you. I'd like to say thank you to my team, because they're always working on the system and they're helping and they make it a reality. Very clever people. Of course, my managers and all the researchers and engineers at Avast, which they always provide thoughtful feedback, a bunch of smart people. And lastly, but not least, I would like to say thank you to everyone who attended this presentation, and I'm looking forward for all the questions you may have, and you can reach out to me anytime. Thank you so much for your time.
Thanks, Joao. I think it was a super engaging talk with all these challenging pipelines you built. It sounds like you did there.
Thank you.
Before we get to questions, if you'd like to leave your feedback for Joao's talk, please fill out the session poll. And now let's get to the questions. So starting from the beginning, Bushan is curious about how you're keeping up with the new patterns of phishing attacks. Like, do the historical attacks and the trained models help to find new patterns of phishing attacks, or I don't know, how often are you retraining? Probably, I don't know. How would you like to answer this question?
We have many systems in place. Some of them is based on computer vision, for instance. And for a detailed talk about some particular projects about this, I challenge you to check the data summit talk from last October we did, where we go in details into the maths stack, which maths stack for us is where we started. Actually, MLFlow, Airflow, TensorFlow, and so on is where we started. And in that presentation, we go in detail on how it's phishing and how it relates with MLOps. So there will be a better way to learn about that.
Okay, thank you. And another question, the alibi tool you mentioned, this is Seldon's alibi, right?
Correct.
Okay. And Kevin asks,
what about that is that we're having a lot of fun with that, with Alibi, with Seldon Alibi, because it has so many algorithms, it has so many interfaces and solutions. Some of them we have a black box approach, some of them you actually need to provide the model. So it's very flexible for different kinds of algorithms you want to apply.
Okay, great to know. And Kevin asks if you can share that diagram, but the slides, I think the talks will be shared in a couple of weeks. But if you want to explicitly share that diagram, Joao, maybe you can paste, if you have a link, shareable link, you can paste it here in the chat for folks.
Okay, I can share the presentation and put it online. Yeah,
okay. And Satyan asks, the relevancy of golden ratio in machine learning. Can you please explain a little bit more?
Sorry, could you repeat the question?
The golden ratio in machine learning, the relevancy of this. He says he missed that part.
The relevancy, okay. So the golden ratio is the perfect form, right? And it's across the ecosystem, it's across our environment, it's in our ears, it's in our face, it's everywhere, right? So we had to identify our where and what do we actually need it to build to make it useful, right? And so initially it was called the golden path. Maybe it's a better naming for that. What would be the golden path for us to bring value to Avast through MLOps tooling and whatnot? So, but for this talk, I thought about, because it's architecture related, and in fact, using golden ratio as in what is it that you're looking for in a form or in a shape. That's what we were at the moment, at the time, is what we were looking for our solution. That's the connection. There is no mathematical connection or anything of such.
Cool. So the other sessions might be starting, but I personally am curious about something. So if for folks who want to stay, I want to ask this question. What was the most challenging part for you to build this pipeline? Like, what was the thing that you underestimated and it took longer than you expected, or turned out to be more problematic than you had expected? As a tip for people who want to build this themselves, maybe you can share some tips if you have any.
Yes, like the most challenging for us at the beginning was actually making people understand our vision. Because before we start building things, in the beginning of the talk, I was talking about the environment, because when you architect something, you need to study the environment where you build on. And we were doing that, and it was very challenging to talk to people and explain our vision. For example, to say, want to have this sort of YAML file that describes things and just gets deployed in cluster A, cluster B. So that was the biggest challenge. So that what we ended up doing at some point was we adopted the MV4 quote when he says, if I ask people if they want to start, they want the horses, right?
Right.
So at this point, we just decided, okay, I don't think people really understand our vision. So let's make one particular machine learning pipeline as a POC and demonstrate the value that it has. We measured the time it took to produce it, uh, and then we presented the final product to the audience, to the company, and then after that they understand, aha, okay, I like that, and then they start to
Yeah.
do that. So there is a challenge. There are sometimes when you are doing the research, you might want to actually do some POC or do something that proves the point, because some people might not have the vision that you are having at the time.
Mm-hmm.
Uh,
Yeah, I like your perspective. That's
Perspective.
super
And from the
innovative.
technical point, the challenge, the big challenge we had, I think that it might be particular to us, is that our build ecosystem, so our TeamCity, our continuous deployment and integration, is
Mm-hmm.
very, very extremely close. So you cannot just build anything. There are some rules, there are some limitations to work within those confines. So when you're building something like that, start asking your release engineering team what are the constraints you might find.
Mm-hmm. Got it. Thank you. I think we don't have any more questions, and we can wrap it up here. So thanks again for your great talk, Joao.
Thank you
And
so much for the
yeah,
invitation, for the great and seeing.
of course, happy to do that. Okay then, and thanks for everybody who's joined, and see you later.
See you later. Thank you so much.
Thank you.